So now let's look at a more complicated Metropolis-Hastings algorithm. Specifically, we're going to look at a component-wise Metropolis-Hastings algorithm where we assume our data come from a normal mu sigma squared distribution, and both mu and sigma squared are unknown parameters of interest. And if you remember from the notes, the component-wise Metropolis-Hastings algorithm essentially means that you implement a Metropolis-Hastings step for each component individually. So in this case, and Metropolis-Hastings steps for the mu parameter and then one for the sigma squared parameter. You do that for both parameters in each cycle, and then you iterate through the appropriate number of cycles. The data that we're going to use to apply this algorithm to is the MIDGE data, the fly data that we talked about or learned about earlier in the course. And so if you recall, the data distribution for the data, which is actually 9 observations, is IID normal mu sigma squared. And then the prior distributions are, one is conditional, one is unconditional. So the conditional prior distribution for mu given sigma squared is going to be normal with a mean of mu naught and a variance of sigma squared over kappa naught. And we're going to set mu naught equal to 1.9, kappa naught equal to 1. Sigma squared has an inverse chi-square distribution with nu naught degrees of freedom, and sigma naught is the scale, with nu naught equal to 1 and sigma naught squared equal to 0.1 squared. So we have our two prior distributions. Our jumping distributions are going to be related to our prior distributions. So the jumping distribution for mu star, so the new iteration or the new sampled value mu star, conditional on mu of t minus 1 is going to be normal with a mean of mu t minus 1 and a variance of sigma mu squared, where sigma mu squared is 0.2 squared. And then the jump distribution for sigma squared is going to be inverse chi-squared with degrees of freedom nu star and scale s star, where nu star is equal to 2 and s star squared is equal to 0.1 squared. So we now have the data distribution, the prior distributions, and the jump distributions, and this is all the information that we need essentially to implement the algorithm, assuming that we have the data. So let's look at the R code where we're going to actually implement this. So the first part here is just sort of describing what we're going to be doing, and we need to load the special distributions from my faculty webpage to sample from the inverse chi-square distribution, though you could use some other package to do that if you wanted to. We're going to load the CODA library so that we can do some MC diagnostics to assess the convergence and run length of our chains. I'm setting the prior parameters here, so mu naught, k naught, which is kappa naught, nu naught, and sigma naught. So these are the parameters for the prior distributions. Now I want 100,000 iterations in my chains. Here I'm reading in the observed data. I obtain the length of the observed data, and then I'm setting some values like S, which is the standard deviation of the observed data, and M, which is the sample mean of the observed data. So now I'm going to have this component-wise Metropolis-Hastings function here, and it takes B, which is the number of iterations desired. It's going to take start, which is going to be the starting values for mu and sigma squared. It's going to take jump.parm1, which is going to be the scale parameter for the jump distribution of mu, and then jump.parm2, which is going to be the degrees of freedom and scale parameters for the second jump distribution for sigma squared. And once I pass those to the function, I sort of pull the relevant components out. So you see I have mu star.sigma, so this is the standard deviation of the normal distribution for mu star. I have the degrees of freedom parameter for sigma square star and the scale parameter for sigma square star. And I'm going to need an object to store all of the iterations for my two parameters. And so I'm going to create this matrix called theta, and it's just going to be a matrix of zeros. It's going to have b plus 1 rows. The reason I have b plus 1 is that the first row will be for the starting values, and then the number of columns is going to equal 2, which is going to be the number of values I give in my start vector. So now that I've put my starting values in place in the first row of theta right here, I need to start actually implementing my component-wise Metropolis-Hastings algorithm. And so in each cycle, what I'm going to do here is I'm going to sample mu star from the jump distribution for mu. And if you remember, that was a normal distribution with a mean of theta I minus 1. So with a mean that corresponded to the previously sampled value of mu, which in this case is going to be found in theta I minus 1 so row I minus 1, column 1, and then the standard deviation is mu star dot sigma. And now that I have sampled mu star, I now need to compute my log acceptance ratio and decide whether I should keep the sampled value. And so I have this complicated set of commands here, and I'm actually going to go over here to OneNote so you guys can hopefully get some more insight into what's going on. So in general, the numerator, and I want to be very clear, this is only the numerator of my acceptance ratio, is going to be the unnormalized posterior density, so Q, evaluated at theta star, the most current values of my parameters that I've sampled from my MC chain, conditional on the data. And I'm going to divide that unnormalized density by the jump density evaluated at theta star, which is the most current values of my parameter values sampled in my MC chain, conditional on the previous values in my MC chain as it's relevant. And because we have two components in our component-wise Metropolis-Hastings algorithm, I'm going to do this twice. Once when the jump distribution is a normal, that's for the mu parameter, and once when the jump distribution is inverse chi-squared, and that's going to be for the sigma squared parameter. So in order to get more insight into computing this acceptance ratio, what I'm going to do here is I'm actually going to write out in slightly more detail what the numerator of our acceptance ratio is going to be. And so the likelihood function, because my data are IID, is going to be the product of the marginal densities, which are normal, and I'm going to compute the normal density for each observed data point. And because I am going to be conditioning on the most recently sampled values of my parameters, I'm going to condition on mu star, which is the value I just sampled in my MC chain. And then the most recent value for sigma squared is actually going to be sigma squared of t minus 1, because I'm actually going to be in iteration t, or iteration I, in the R code. And because I'm in the current iteration and I haven't actually sampled a new value for sigma squared, I have to use the value that was sampled in the previous cycle or previous iteration of the chain. And so that's why I'm conditioning on mu star, the most recently sampled value of mu, and then sigma squared of t minus 1, the value of sigma squared sampled in the previous iteration of the chain. And then now I need to multiply the data distribution by the prior densities, or the prior distributions. And so the prior distribution for mu is a normal with a mean of mu naught. And then if you remember, the variance of the normal distribution was actually conditioned on a known value of sigma squared. And we once again are going to be conditioning, we want to use the values that were most recently sampled in our MC algorithm. And so I'm going to evaluate this normal density at mu star, which is the value of mu that I just sampled in my MC chain. I condition on the mean mu naught, and then the variance is actually sigma squared over kappa naught, right? But I'm conditioning on sigma squared being equal to sigma squared of t minus 1, the value I sampled in the previous iteration of my chain. And the reason it's not the current value is because I haven't actually sampled a value for the current iteration of my chain. So this is actually still conditioning on the most recent value of sigma squared that I've sampled. That was only the first part of the prior distribution. We also still have the part of the prior distribution related to sigma squared, and that's going to be inverse chi-squared. I evaluated at the most current value or the most recently sampled value of sigma squared that is in my chain, which is sigma squared t minus 1. That was what I chose sigma squared to be in the previous iteration of my chain. And I'm going to condition on the degrees of freedom parameter nu naught and the scale parameter s naught that I specified in my prior distribution. So this whole part right here is all just related to the Q function, the unnormalized posterior density. And now I need to divide that by a density related to my jump distribution. In this case, it's the jump distribution for mu. And so if you remember, the jump distribution for mu star was normal with a mean of mu t minus 1, so the value that I obtained in the previous iteration of my chain, and sigma mu squared, which I set to be 0.2 squared, I believe. And so I want to evaluate the density, that normal density at mu star, the most recently sampled value of mu, conditional on that normal distribution having a mean being equal to mu of t minus 1, the value of mu selected in the previous iteration of my chain, and sigma mu squared, the the variance parameter for that jump distribution. And one thing I want to point out here is that because we have a product of IID normal distributions here, IID normal densities, when I compute the log acceptance ratio, I'm going to have the log of that product. And if you know the properties of the natural logarithm function, the log of a product is going to be the sum of the log of the individual elements of that product. And so when I apply the log to this part of my acceptance ratio, I'm actually going to get the sum of the log of the densities for the individual random variables. So now let's go back to our chain here and see how we actually program this up. And so you can see I'm just looking at the log numerator part of my acceptance ratio here. And so I have the sum of the log of those marginal densities. Notice that the mean is mu star, the most current value, the value of mu that I just sampled from my jump distribution. And then my scale parameter, my standard deviation, is sigma squared of I minus 1. So the value of sigma squared that I chose in the previous value of my chain. I take the square root because that's how R parameterizes the normal distribution. So this is the data distribution part. And then I need to add to that the log density for the conditional prior distribution of mu conditional on sigma squared. And so I have the log and then the normal density. It's evaluated at mu star, the value I just sampled for mu. And then the mean of that prior distribution was mu naught. The standard deviation, remember, was conditional on the known value of sigma squared. And the most recent value of sigma squared that I have in my chain is in column 2 of my theta matrix. And it's in position I minus 1 because I'm actually in iteration I of my chain. And so to get the previous value of sigma squared, I look in row I minus 1 of that matrix. And then I divide by k naught, which was the other parameter that we used in our prior distribution for mu. And now I need to continue by adding to that the log prior density for the sigma squared parameter is an inverse chi squared. I evaluated at the most recently used value in my MC chain for sigma squared, which is once again in column 2, row I minus 1, because I haven't yet updated the sigma squared parameter in this iteration of my chain. And then the degrees of freedom of that prior distribution was nu naught. The scale parameter was sigma naught. So this whole part right here is related to my unnormalized posterior density. And now I need to correct that by the jump density. And so I'm going to divide by, I subtract the log density of the jump distribution. And the jump distribution for the mu parameter was normal. I'm evaluating it at mu star. The mean of that jump distribution was the mu used in the previous iteration of my chain. And the mu parameters are in column 1 of theta. And to get the value in the previous iteration, I'm going to look at row I minus 1. And then the scale parameter is mu star dot sigma. And so this is the numerator of my log acceptance ratio. And I'm not going to say a lot about the denominator here, except that everywhere I have a mu star, I'm going to replace with the previous value in my MC chain for mu. Okay, so everywhere I have a mu star, I'm going to replace that with mu of t minus 1, the value of mu that I used in the previous iteration of my chain. And then everything related to the sigma squared parameter is actually going to remain the same. And so I make those replacements, I compute the denominator. That allows me to compute my log acceptance ratio for the mu parameter. And then I go through the process of deciding whether I'm going to keep the value of mu star I proposed, or whether I'm going to update the current iteration of my mu parameter, the current iteration of my chain, for the mu parameter with the previous value in my chain. So that's what I'm going through here. I'm trying to decide whether I update it with the proposed value or I keep the previous value in my chain. Okay, so that is the Metropolis-Hastings steps for mu, but now I need to do something similar to sample a value of sigma squared. And so I sample a value sigma squared star from my jump distribution for sigma squared, and that was an inverse chi squared with this degrees of freedom and then this scale parameter. And now I need to once again compute my log acceptance ratio for this chain. And it's actually going to look very similar to what we had before, but just to describe this in a little more detail, because there are some slight distinctions. I want to compute the I want to compute the unnormalized density evaluated at, I want to compute the unnormalized posterior density evaluated at the most recent values in my MC chain. I'm going to divide that by something related to the jump distribution for the parameter of interest in this step. So for the data distribution, I once again have that product of the normals. Okay, but notice here that the values I'm conditioning on is different than what I conditioned on before. I'm going to condition on mu t, the value of mu that I selected in the current iteration of my chain. So the one I actually, not necessarily that I just sampled, but the one I actually end up keeping. So it might be mu star, it might be mu of t minus 1, depending on whether I accepted the proposal or not. But this is the value that we have updated mu to be in our chain at the current time step. So that's going to be the mean of my data distribution. And I'm going to scale that normal distribution by sigma squared star, the value that I just sampled from my proposal distribution. Similarly, when I evaluate the prior density related to mu, I'm going to evaluate it at mu t, which is the most recent value of mu in my chain. And I'm going to condition that on mu naught, which is the mean parameter of the normal prior distribution, and then sigma squared star, which is the value that I just sampled, the value I just sampled for sigma squared from my jump distribution for sigma squared. And I'm going to multiply that by the prior density for the sigma squared parameter. Once again, I'm going to evaluate this at sigma squared star, the value that I just sampled from my proposal distribution, my jump distribution. I'm going to evaluate at the prior parameter values nu naught and s naught squared. And now that I have the numerator of my acceptance ratio, I need to scale that by a quantity related to, a density related to my jump distribution. And the jump distribution for sigma squared was inverse chi squared. I'm going to evaluate that at sigma squared star, the value that I just sampled from my jump distribution. And the parameters I'm going to use for that density are mu star and sigma star squared, which are the values for the jump distribution of sigma squared. And notice here that I actually am not conditioning on the previous value of sigma squared in my chain. And the reason is because I actually chose the jump distribution for sigma squared to be an independent sampler. So it actually does not depend on the previous value that I sampled for sigma squared in my chain. So now I can go back to my R code and look at this in more detail. And so essentially I'm doing the exact same thing I did for the log acceptance ratio of mu, except that everywhere I had a mu star before, I'm going to replace that with theta I minus 1, which is the mu that I selected for the current iteration of my chain. And everywhere that I had a sigma squared of I minus 1, so when I was using the value of sigma squared selected in the previous iteration of my chain, I'm actually going to now update that with sigma squared star, which is the value that I just sampled from my target, or I'm sorry, not from my target, from my jump distribution. So this all looks very similar to before. I'm just making those relevant updates, and then I'm evaluating my jump density at sigma squared star using the corresponding degrees of freedom and scale parameters for that jump distribution. And then the denominator is actually very simple to calculate once I have correctly outlined the numerator. Everywhere I have a sigma squared star, I'm going to replace with sigma squared star, or I guess to say sigma squared of I minus 1, the value that I used in the previous iteration of my chain. And so you can see that's what I'm doing here. So sigma squared, that was in the second column of theta, and to select the value in the previous iteration, I look in row I minus 1, and otherwise, everything else is the same. So everywhere I had that sigma squared star, I replace that with theta I minus 1. And there actually are no, I actually didn't use the previous value in my chain anywhere in the numerator. And so I don't need to make any other changes when I'm computing the denominator of my log acceptance ratio. So once I have computed the numerator and denominator of my log acceptance ratio, there's actually a typo here. There's actually a bug here, which is bad. So this will be interesting to see how this makes a difference. But R should be set to numerator.r minus denominator.r. And then once I have the log acceptance ratio, I generate a value from a uniform 0, 1 distribution. I take the log of it, and I accept it if that value is less than the minimum of r and 0. And if I do accept, then I update the current value for sigma squared to sigma square star, the value I just sampled from my jump distribution. Otherwise, I actually just update it with the previous value in my chain. So I had run this before, but we're going to need to run it again, which is okay. And so I'm going to run 3 chains, and the jump parameters are all going to be the same, but I'm going to use different starting values to explore the parameter space in a little bit more detail. So I run that code. Hopefully it doesn't take too long to run these chains. So now that I have the 3 different chains completed, I can run some convergence diagnostics to decide whether the chains converge to their stationary distribution or whether I've run them long enough. So I'm going to keep the second half of each chain. So I'm going to use a conservative warm-up period, and then I'm going to take those values and create an mc.list object. Now I'm going to look at a trace plot of the 3 chains for the 2 different parameters. That's going to show up over here on the right-hand side. So this is actually the trace plot for my sigma squared parameter. We actually see a lot of movement here, which looks pretty good. We definitely have some larger values, but overall this doesn't look too bad. And if I look at the trace plot for mu, we see a lot of movement, which looks really good. We see basically the chains are falling in the same place, and so this makes it look like perhaps our MC chains have converged to their stationary distribution. Let's look at some autocorrelation plots of the chains. So here is the autocorrelation plot for mu and then for sigma squared. We actually see they look pretty similar. My lag, so the values in my chains are correlated out to maybe 10 or 15 iterations, something like that, which could be better, but could be a lot worse. So this is not terribly bad news. So that was for the first chain. The second chain looks very similar, as does the third chain. And so we get similar results there. Now we can look at our effective sample size. So we sampled 100,000, we did 100,000 iterations in each chain. We kept half of them, and we ran 3 chains. So we sampled 150,000, or we ended up looking at 150,000 values in the combination of our chains. So that's sort of the baseline standard for our effective size. We run the effective size function here, and we have about 27,000 effective samples for the mu parameter and a little over 41,000 for the sigma squared parameter. And so this is actually not too bad. We had 150,000 in our chain, so we would have liked to see these numbers be higher, but we still have a pretty decent effective sample size with which we can estimate our posterior distribution. So looking at the Gelman-Rubin statistic for the 2 different parameters here, so the parameter for mu and for sigma squared, the r-hat statistic is very close to 1. In fact, the upper confidence interval, the upper limit of the confidence interval, it reduces to 1. So in terms of decimal places and things like that. So at least using the Gelman-Rubin statistic to assess convergence, it appears that we have in fact converged to the stationary distribution. We can look at a plot of the r-hat statistics for the 2 parameters as a function of iteration. And so this is for the mu parameter, this is for the sigma square parameter, and it looked like we converged very quickly for the mu parameter to a small value of r-hat, and for the sigma squared parameter it actually took quite a bit longer, and so we needed to run our chains about as long as we did in order to converge to the stationary distribution. At least that's what this particular diagnostic is saying. For the Heidelberger and Welch diagnostic, we're going to look at whether we converge the stationary distribution and whether we can estimate the posterior mean with the desired level of accuracy. So we have both tests for each chain, and we passed the stationarity test for both parameters in each chain. We also passed the half-width test, and so we have converged to our stationary distribution, and it appears that our posterior mean can be estimated with a pretty high level of precision. So now we can look at the Raftery-Lewis diagnostic to see if we can estimate quantiles accurately. So we run that diagnostic tool and we get results for each chain. So once again, it says that we don't have to drop very many observations for burn-in, which makes sense since we've already done that to a certain extent. It says that we need about 17,000 iterations to get the desired level of accuracy for mu, and we actually have way more than that. We have 50,000 iterations in each chain, so we have in fact met this criterion for the Raftery-Lewis diagnostic, and we actually need fewer iterations for the sigma square parameter, and so we have more than enough samples, more than enough iterations in our chains to estimate this quantile with a desired level of accuracy. So that's good news. And if we look at our Giwiki diagnostic, where we're comparing whether the mean for the first part of the chain is equal to the mean of the second part of the chain, I expect to see good results in general. So once again, these are z-scores for a z-test, and so we want to see these values be between -2 and +2. When we look at the results for each chain, that's exactly what we get. And so essentially for all the tests that we did, for all the methods, all the diagnostics that we looked at, it appears that our chains have converged to their stationary distribution, and we have run the chains long enough to get a relatively high level of precision in estimating quantities like the posterior mean.